at e to the minus ipx plus a different operator for the antiparticle bp dagger e to the ip. You can work out that the commutation relation between phi and its canonical momentum will have the standard form if A's and A daggers are creation and annihilation operators, B's and B daggers are creation and annihilation operators, and A and B in all forms commute. Okay, this you should just verify. I won't do that. So you could have done exactly the same way we have proceeded for the real scalar field. You could have imposed the commutation rules on the phi and pi and could have discovered this. The reason I am emphasizing this is that this work for real scalar field, it is working for complex scalar field, it will fail for electromagnetic. Okay, this idea will not work. Okay, and you have to do various other things. So that is why I am emphasizing. You could have also decomposed this into harmonic oscillators. In this case, in some sense, it is easy because if you take phi and you expand it as qk e to the ik dot x, since phi is not Hermitian, the qk's are just sort of floating in the air. I mean, there is no condition between qk and q of minus k, so qk's are complex numbers with a real and imaginary part, and you can work everything out, and all the processes which you have thought of will go through. In particular, if you go and re-express the Hamiltonian in terms of these fields, you will find exactly what we have found before. You will find that the Hamiltonian can be written as, there will be a contribution, so let me write this as d3k upon 2 pi the whole cube, and both the real and imaginary parts will contribute, and you will have, if you eliminate the 0 point energy, you will end up getting omega k times the number of particles, which will be ak dagger ak plus bk dagger bk. Where ak and bk are related to these by that square root of 2 omega factor. Okay, so that is taken care of here because this is d3k, but this has that 1 over 2 omega. So everything will work out. Now you can think of them as a set of particles and a set of antiparticles, and at any given particular state is constructed by giving the number of particles and number of antiparticles. This is the way the whole formalism will work. So how do you distinguish between these two? For that you need some other operator, and that is what I am going to spend time on because that is a new feature which was not there in the real scalar field. So this is an introduction of a charge operator. And we found that this particular Lagrangian, this has been done before, so I am just reminding you, this particular Lagrangian has an invariance under phi going to e to the minus iq alpha phi and phi dagger going into e to the iq alpha phi. It's some constant alpha here. So if there is, you take the infinitesimal version of that, then delta phi is minus iq alpha times phi, and delta phi dagger is this quantity, and because of that symmetry there is a conserved current. So we found that the conserved current can be written as, you should go back and refer to your notes, some JL, which is essentially pi L for the fields, which I will denote by some capital A, delta phi of the fields summed over A. Okay? In this particular case, this A goes for phi and phi dagger. So delta phi from this is going to be minus iq. You eliminate the other part of it, so iq times phi. You don't really put this alpha because it is all defined only with respect to a total proportionality constant. So this, then you have to take the pi for the phi field. Pi for the phi field is this, with the zeroth component being given by this, So you are going to end up getting, so let me just write down the J0 component, that is easier. So that will be just this pi. So this is phi dt of phi dagger coming from this. Then you will have the delta phi for the phi dagger field, which will have an opposite sign. So it is plus iq phi dagger dt of phi. So the charge is going, the charge density, so to speak, the zeroth component is iq phi dagger dt of phi minus phi dt of phi dagger. I think the sign is correct. If the sign is wrong, we will flip the sign of q. So q is just an arbitrary parameter here. So you get a structure here. This is a new object. This is a conserved current. JL is a conserved current. So there is a charge associated with that conserved current, which is q integral over, let us say, d3x of J0 of t comma x. Now, of course, since it is conserved, it doesn't matter at what t you are evaluating it, but this is an operator because J is now going to be an operator, these are going to be an operator. One would like to know how this operator looks like in terms of A's and A daggers. Just like when you had the Hamiltonian, which was an integral over d3x of some Hamiltonian density, which you remember was something like phi dot square and pi square and an m square phi square term. Here, instead of that, you have again a bilinear quantity with one derivative acting in between. Okay, this we would like to compute. I am going to do that in a minute, but before that, I wanted to get some general results about charges and currents, because that is going to be very important in various aspects in particle physics. Suppose you have a generic symmetry transformation. I am not specifying what it is. I am not saying it is going to be exactly this. Some delta phi A is generated with this pi, and you have a current density or a charge density like this. Then there are a few comments which you can make about that. The first thing is, suppose you compute the commutator of, let us say, q phi. Okay, that is going to be, if q is going to be integral, let us take it as d3y now, because I would like to keep phi at x. d3y, the pi for that field, and in fact I can even put some thing here. So this is pi for some component b, because it is being summed over again, so I am using a dummy index there, times delta phi of b. These things are evaluated at y. So this integral is what defines for you your charge q. And I have to do the commutator of that with respect to phi. Okay? So you end up getting this commutator. You think of these as parameters. So there is a phi b at evaluated at y commutator at the same time. So this is t comma y phi commutator t comma x. Okay, this by definition we know is going to be Dirac delta function, but because it is phi and a pi is I times Dirac delta function, this has a flip of sign. So this is going to be minus I. There is a Dirac delta function on y minus x. This is evaluated at y and integrated over dy. So that is going to give you x. So you get delta phi a at x. How did this a appear? When you do this, I am going to do the commutator between these two. And if these two are two different fields, then they commute. So there is also a Kronecker delta on BA. That acting on this B will give you the Kronecker delta. Okay? So this is a very general result, and I am sure you have seen this in different forms, but you might not have realized it. What it tells you is that you can think of this Q as a generator of a symmetry transformation. So the generator of a symmetry transformation, when commuted with an operator, produces the change in that operator. For example, if you think of time translation, the generator of a symmetry transformation which you think of as time translation would be the Hamiltonian. So the Hamiltonian, when it commutes with some object, will give you the change in that object, a time rate of change in that object. Similarly, if you think of spatial translation, the same thing applies. So this is a very general rule, because whenever there is a symmetry transformation which is available, you get a conserved current. And once you have a conserved current which has this structure, if the commutation rules work, then the commutation rules will give you this. This is one of those profound results which can be derived very easily. I mean, it doesn't require too much of a work, but it is never sort of stressed in that form. So this is given any symmetry, you have a conserved current and charges, and the local version of that, when you do the commutator with the local operators, it will generate the changes in the operators, which is exactly what you would expect. So it closes the loop. Okay. So whenever you have any such charge, it produces some change which is obtained by this. Now I want to use this to produce one very interesting application of this, which is our old friend, which we call the Goldstone mode and the Goldstone's theorem. We said that whenever you have your system, we studied it in the context of the symmetry, a potential Vf for a complex scalar field which had a minimum along a circle. So we are again studying the same complex scalar field, except that the potential has been changed. Suppose I have been working with a Vf kind of potential. Then if you remember, that potential, you think of phi 1 and phi 2, the real and complex parts of the field as two axes. Then the potential was a minimum on a circle. Then we studied this with a transformation on the field. We found that there are two kinds of modes. One kind of mode is which is oscillating around that minimum, which had a mass, and the other is the one which is rotating on that valley, and that is a massless mode. At that time I told you that this is an extremely general result. Whenever you have a symmetry which takes the state of the system from one point to another, in this particular case of that complex scalar field which we are talking about, if I think of phi 1 and phi 2, so the potential is in this direction, okay? So there is the phi 1, phi 2 plane, and the potential has that curvy shape there. So it has a minimum at some value, we used it as a radius v, and here is the value. Okay, so you should imagine that the potential has a minimum here, a maximum here. Think of it like contour lines. So if I move from here to here, I don't have to spend any energy, and that is a massless mode for me. But what does that mean? Changing from one point to another is just rotating in phi 1, phi 2 plane, which is exactly this kind of transformations. Right? When you do, I mean, you take a sine alpha times phi 1 and a cos alpha times this thing. So in terms of phi, it is just a rotation. You change the phase of that. So this current which is being conserved is essentially coming from this rotational invariance, which is U1 invariance of the theory. But we know that a state here, a state here, a state here, all these states have the same energy. Okay? So let us extract the key idea out of it, and then let us see whether we can prove this theorem at great generality without having to use a specific form of the potential, change of the transformations, etc. The way the proof goes is it is possible, and it is known as the Goldstone's theorem, which essentially tells you there will be a massless mode in the theory. So what we are thinking of is that there is a Hamiltonian and there is a ground state of the Hamiltonian with let us say 0 eigenvalue. Okay, the ground state energy we normalize to 0. Now what you do is that you think of operator Q, which is a charge associated with that symmetry. So the first thing you know is that the Q commutator H is 0 because the charge is constant. So it commutes with the Hamiltonian. Now you look at this state Q on the value. Now this is going to be a state. It could happen that Q on the vacuum gives you 0. So the vacuum has 0 charge. On the other hand, this Q, which is like the generator which changes the delta phi, could be changing the state from one state to another, like which happens here. So the ground state can be degenerate, and there could be several states, all of which has the same energy. So it can commute with this, but this could also have the same energy. Okay? Now the question is, suppose that is what is happening, can you show that there is a massless mode? Alright. So we have said that there are states like this which has 0 energy, but these are not the unique state in the sense that there is a degenerate circle of states here in this particular example, all of which has this 0 energy. The way the proof goes is the following. You start by constructing an operator which I will call integral over d3x e to the, let us see, in our signature convention I think it should be I k dot x. So it is I k x J0 of x. Let us look at this operator. If k was 0, this is just a charge, right? In the limit of k going to 0. So I am going to look at it with k not equal to 0, and I am going to show that when k goes to 0, the energy of the state will vanish. If that happens, there are this is like the momentum. And the momentum and the energy has a dispersion relation where when k goes to 0, E goes to 0. That is the relativistic definition of a 0 mass state. Think of omega square as k square plus m square. If there is a no mass gap between these two, you say that there is a mass. This is what we are trying to show. So to do that, first I want to calculate what is the momentum of this state. Because this momentum is claimed to be k, so that needs to be proved. So you look at the operator P alpha acting on this state, that is, you first think of, okay, let me call this as some state S, okay, which is obtained by acting this on the vacuum. Now I want to look at P alpha acting on this state, so P alpha on S. You have a question?
Sir.
Yeah.
So why are we looking at the k goes to 0? It will give us.
Okay, so I want to show that if these conditions are satisfied, there is a 0 mass mode. So I need a definition for the 0 mass mode. A 0 mass, if you think of a dispersion like just to give you an example, dispersion relation like E square equals k square plus m square. Then when k goes to 0, you will have a value m. If m is 0, if there is a 0 mass mode, then when E goes to 0, when k goes to 0, E should go to 0. So we want to prove that there are states with a momentum k, such that when k goes to 0, the energy of that state continuously goes to 0. That is where we are looking at that. So let us look at P alpha of S. So P alpha of S will be, I will have to put a P alpha here. Okay. Now I use the fact that ground state has 0 momentum. Therefore, whether I put a P alpha here or a P alpha in front, the second term will vanish. Therefore, I can replace P alpha J0 by a commutator of P alpha J0. That is, I claim this is equal to integral d3x e to the I kx P alpha commutator J0 acting on the vacuum. Let us make sure we understand that. One way is to just look at this. This has a P alpha J0, which is exactly this quantity. Then it has a J0 P alpha, but P alpha acting on the ground state gives me 0, because the ground state has 0 energy and 0 momentum. Okay. So you have got this. Now what is this quantity? This quantity we know. This is given by minus I d alpha of J0, which in our notation will be equal to plus I d alpha of J0 because we want this to be at the bottom. Okay, so you plug it in and you end up getting integral d3x e to the ikx. This entire thing is equal to, so keep an I outside, d alpha of J0 acting on this. Now you play our usual game. You take the total divergence of this. So this becomes d alpha of that whole thing. That integrated you ignore. So you are going to end up getting a d alpha acting on this term with a minus sign. Okay, that is going to be I k alpha. So that is going to be k alpha. I and a minus sign will take care of itself. Integral d3x e to the I kx J0 on this. But this is exactly what we have got here. So this is equal to k alpha s. Right? Let us make sure we understand that. You first see, the only clever thing in this argument is construction of this state. Once you have got that, everything else is algebra. You start from the ground state and you construct the following state, which you call state S. Then you show that this state S is the eigenstate of the momentum operator with momentum value Kr, which is what we have done. So when you do this, first there is this trick of using that the ground state has zero momentum to get the commutator. Then you use the fact that generator commuting with an operator gives you the derivative of that with respect to that variable. Then this is just algebra, and you throw away the total divergence, and then you end up getting this k alpha, and everything else goes for a run. So you end up reproducing the same state you started with. As a result of which you have got this as the eigenstate here. So we know that this state, yes, has this label k. It is not just a label, it represents the physical momentum of that state. Rest is obvious. If you now go back to this and you look at the limit of k going to 0, you end up getting a state. So suppose I take this state and you want to know what is the energy of this state. So the energy of this state is h acting on this. Let us see what it will give, whatever is the eigenvalue. But since h commutes with q, this is equivalent to just flipping. It is q h 0, which is 0. Therefore, the energy of this state is 0. Right? I mean, which is essentially saying that they are all degenerate. Now, if I look at this state, we know that the k going to 0 limit of the state S is going to be just integral d3x j0 of x acting on this, which is nothing but your q acting on vacuum state. Right? And this state we just showed has 0 energy. Therefore, if you take this state and you vary k and you take k to go to 0, in the limit of k going to 0, that state will have 0 energy. This is the massless mode. Okay. Now, the beauty of this argument is that it does not ever use relativity. Okay, I never said that it is a relativistically invariant system or a field theoretic system or the Hamiltonian has a particular form or the potential has a particular form, any such thing. So, in that sense, it is, of course, the notion that you have a massless excitation comes from relativity, where you have omega square is equal to m square plus k square and you take this limit, etc. But the same kind of systems will exist even in non-relativistic theories. That is, you will have states such that when the momentum continuously goes to 0, the energy will go to 0 and that mode will exist. Of course, its real use from our point of view is in studying field theory. where if there is a symmetry which produces this degenerate state. So the whole point was that you have now two states, Q acting on the, if Q acting on the vacuum was 0, then it doesn't help. You want that to produce a different state. And then that state, from that state you can construct this sequence of states. And when K goes to 0, this sequence of states will have 0 edge. Okay, this is what you do. Okay, fine. Now, the next step which we want to do is to look at the explicit form of Q in terms of A's and A daggers. I said we will come back to that, so let us finish that. This is again a bit of a boring calculation which we have already done. It is almost like what we did for Hamiltonian. You have to essentially take this, take its Hermitian conjugate, then you have to go and compute this quantity in terms of A's and A daggers. Okay? So I will indicate how the analysis goes rather than do all these steps. Fine. So let us start with that phi of x, and then I want phi, the derivative of that, and then I need phi dagger. So let me write down the expression for phi dagger. So the phi dagger of x is going to be some d omega q So here you will have AQ dagger e to the IPX plus BQ, sorry, this is Q, IQX, BQ e to the minus IQX. Okay. Now we want to compute this quantity. Let me do it here itself. Okay. So let us look at that first term. So I have IQ. There is a phi dagger and a dt of phi. So phi dagger is going, so there is going to be a d omega q, then there is a d omega p, that is going to go for a right in both the terms. Then phi dagger is going to have these terms, so let me write them down. AQ dagger e to the IQX plus BQ e to the minus IQX. This is going to be multiplied by dt of phi. So let us evaluate dt of phi. So if I take this and I take the time derivative, in this the time derivative will bring down a minus I omega. So let us write that down. So I have a minus I omega p. After that I will have AP e to the minus IPX. We have taken a minus I omega, here it will come with a plus I omega, so there is a minus sign here. B dagger P e to the IPX. Okay. Now this is the current density which I have written down. It is going to be, you have to subtract this term out of it. So let me take this, you might as well think of this as the dagger of this, because if I take the dagger of this, you will have a same construction with a dagger. So after computing it, if I just take the dagger and subtract it, is fine. Now what is the structure of this? Since we had already done it once, you should be able to guess what we are going to get. You will have first a dagger A kind of a term. and you will have a e to the iqx and e to the minus ipx, and you are going to integrate over all d3x, right? And since it's a conserved quantity, you might as well take t is equal to 0 and just think of these as just having the spatial coordinate. The moment you integrate it, you will end up getting a standard 2 pi factor and a Dirac-Delta function on p minus t. Okay. Similarly, when you take this product and do this, you will end up getting a same kind of a structure, but now you will have a b and a b dagger with a minus sign. Okay. Then there are two cross terms. What you will find is that these cross terms will vanish. That is because the cross terms will have a structure a dagger and a b dagger with a minus sign. So when you go to the dagger of that, that will become a and b. They commute, so it doesn't matter in which order you write down. Similarly, you have a and b, which on going to the other side, taking the dagger of that will give you a dagger, b dagger. Those two terms will cancel. So only the a terms and the b terms are going to survive, and they are going to come with a minus sign. And then when you work everything out, you will find incidentally this minus I and this will go, and a q will survive. And both of these are going to give two copies of each. So there is a factor 2. That 2 omega will precisely cancel with one of the 2 omegas here. Other one will go away on integrating over the Dirac-Delta function. So you work this out, and you will find that the answer is given by now q. The total charge is going to be q times integral over d3p upon 2 pi the whole cube times a dagger of p, a of p minus b of t, b dagger of p. This is important. Because here you will get a dagger a, but here you are going to get a b dagger, and when you do all your commutations etc., this will come with the b dagger. So work this out with one minus sign. Okay, what does this mean? First of all, there is a little bit of an ambiguity here. What we are going to say is that the b dagger, if I flip it around, I will get a b dagger b fine. Then there will be an infinite constant there, which is exactly what we found in the case of Hamiltonian. In the case of Hamiltonian, they will come with plus. When you flip it down, there is an extra contribution, which was the 0 point energy, and we said that this has to be eliminated by normal order. Okay. Then you have to bring it in as an ad hoc prescription, and then normal order it and remove this. Here, if you don't do this, the charge of the vacuum state, if you take the vacuum expectation value of that, the charge of the vacuum state will be infinitely large. So you don't want that. This came up in the discussion last time. This is how that mathematics gives you, which you do not want. So you will normal order and remove. However, here you are in a slightly better position conceptually. And the reason is the following. You notice this J0. Classically, this object would have been a star here and a star here. And that is perfectly fine. Quantum mechanically, once you go into this, you have a dagger here and a phi here, phi dot here, and these things do not come. Okay? So this is like pi and phi kind of a thing. So if we saw just here, did I wipe it out? No. Okay, so look at this. The momenta of the phi is the time derivative of the phi dagger. So that is exactly the combination we have. Time derivative of phi dagger and a phi. So this is like QP. Now whether you write QP or PQ makes no difference in the classical theory, but it makes all the difference in quantum theory because QP is not equal to PQ. Therefore, the ordering of these terms in this is ambiguous. It is intrinsically ambiguous. You are taking a classical structure and you are looking at its quantum version. There is a factor ordering ambiguity here. Therefore, you can choose the factor ordering by some physical criterion. This did not happen in the case of a Hamiltonian, because the Hamiltonian had only terms like del phi the whole square, pi square and phi square. At a point when you evaluate, they may blow up in your face, but they do commute. Phi phi, whichever way you write is phi phi, and same with pi pi, energy of the system. Once you have done that, you can quietly remove this and put a dagger here. Now you see that the extra minus sign which you have got is telling you that if the charge of these A particles is Q, the charge of the B particles is minus Q. This I told you long back. At that time we didn't prove. When you have this kind of a transformation, something goes with Q and something goes with Q dagger. Something goes with minus Q. So the phi and phi dagger, each of them contains a combination of particles and antiparticles. This is something which we emphasized even earlier on. You shouldn't think of phi as particles and phi dagger as antiparticle. That is not true, because if you look at the structure of phi, there is A and B dagger. B dagger is antiparticle operator, A is the particle operator. So there is a linear combination, and we also explained why we need that. But when you compute the charge, it comes with the correct minus sign. As a result of which, you can interpret the particles which are created by B dagger to have a charge which is opposite to the particles which are created by A dagger. So that is why we call it a charge scalar field in the first place. Okay, fine. So you can compute this quantity. There is also one more comment regarding this. When you are doing this analysis in the same sort of way carries forward for any generator. Until this point, we are not sort of brought in electromagnetism. Right? We haven't even put in an electromagnetic coupling. You could have started with this transformation, found a conserved charge, and found that whatever charge you attribute to Q, you have to attribute to the antiparticle minus of Q. In general, you will find that in particle physics, when you are talking about the phenomenology, there are other conserved charges, at least approximately conserved charges and currents which you attribute to particles. Like there are things like lepton number, which is an attribute which you give to something, or a baryon number. All these things come from some symmetry argument. In that symmetry argument, you have Lagrangian which is invariant under some symmetry. There is a conserved current and a conserved charge. And when you second quantize the system, or in the old-fashioned language, or when you quantize the field, these objects will come up with the charges which has this opposite sign. As a result of which, you can attribute to a particle a lepton number, and to an antiparticle negative of the lepton number. So the analysis completely go through, and it need not have a field associated with it. Okay, because this was not done with an electromagnetic coupling anywhere put in. So there is just one more comment which I want to make, because all throughout the course we have not been touching fermions. That is, I never did Dirac equation, because you guys already had one course in Dirac equation, etc. It might not have been done in how to quantize a Dirac field, but at least in semi-classical level you have studied Dirac equation. So if you have a spinor field, the important difference between quantizing a Dirac field and quantizing a scalar field, for example, the electron field and a scalar field, is that in the case of scalar field you use commutation rules. You say that phi and pi commutator is equal to IH cross times the Dirac delta function. When you are dealing with the fermionic field, you have to actually use anti-commutators. Now there are various ways of proving this, most of which is fairly complicated. Any rigorous proof is fairly complicated. But you can do the following, just for fun. You can try to quantize a scalar field with anti-commutator. See, you start with this field, and instead of postulating that phi and pi commutator is equal to IH cross, suppose you have gone and assumed that phi and pi anti-commutator is equal to IH cross. Okay? If you do that, what you will find is, interestingly, the Hamiltonian will pick up a minus sign, and the charge will have plus sign. Okay? So what happens is that the moment you use the wrong statistics, or instead of using commutators, if you use anti-commutators, the Hamiltonian no longer will be positive definite. It can go arbitrarily negative, while the charge will remain positive. But when you use the commutators, The charge is going to have either sign depending on what state you are looking at, but the Hamiltonian will have a positive definite sign. Okay. So this is one way of saying that if you take Dirac equation and the Dirac Lagrangian and all that, and you try to quantize it with commutators rather than anti-commutators, the same thing will happen. The structure is such that the Hamiltonian will become unbounded from below. And this is one of the easy ways of arguing that it should be done with anti-commutator. Okay. So that is another comment which I wanted to make. Okay. Now, I wanted to finish a little early today, but we have some time to just introduce the electromagnetic case. So that is how I want to talk about complex color field. Rest of it you should be able to work out. Now let us look at electromagnetism. So in electromagnetism, just like we started with that Lagrangian there, the Lagrangian we want to start with is minus 1/4 FLM FLM. And we had already seen that this of course corresponds in some gauge at least. So if I make a gauge choice, phi equals 0, this will go into half A dot equals square minus curl of A whole square. This is just E square minus B square. E is minus A dot minus gradient of phi. I am setting phi is equal to 0, so that doesn't contribute. B is curl of A, and this is what. You can immediately see from this that dl with respect to d phi dot, we have discussed this before, is equal to 0, and dl with respect to dA dot is equal to A dot, which is minus E. Okay? What it means in our notation is the following. We are doing dl with respect to d of dt of A superscript alpha. This is equal to minus dl with respect to d of dt of A subscript alpha. Because alpha up and alpha down, alphas are 1, 2, 3, flipped by a sign. And this quantity is what we have got as minus E. So this is going to be minus E alpha. So you get the result that this quantity is equal to E alpha. Okay. This is what we have. So this is our standard notation for E. The flip of sign is taken. Now, how would you go about quantizing this system? Okay. In the generic sense, I would like to impose the commutation rules. You take AL at some time t at some point x, commutator, the pi for that AL, j, let us say, at t at y, is equal to I times Dirac delta function of x minus y. This is our rule, right? So we had two ways of doing the quantum theory of a classical field. One was to go to the harmonic oscillator basis and quantize each harmonic oscillator. The other was to impose this commutation rule, solve for the equations, find the mode functions, identify A and A dagger, and the harmonic oscillator will come out. In the case of real scalar field and complex scalar field, both the procedures were equal. We could have done either one. In the case of electromagnetic field, it will turn out that the method using the harmonic oscillator works. In general, as long as you are not worried about Lorentz invariance and gate invariance and things like that, identifying the nitty-gritty harmonic oscillator is always a sure method of quantizing this system. Because you reduce the system to harmonic oscillator and you know how to quantize the harmonic oscillator. The other method is this, and I wanted to show that this runs into some trouble. These troubles can be handled, but it requires fairly elaborate amount of formalism, which I am not going to introduce because we are going to do mostly with the harmonic oscillators. So if you look at this, and of course there is a delta J, the Kronecker delta, this J. This is what you would have expected. This already tells you that this is nonsensical. All that you have to do is to put L is equal to 0. Right? The corresponding momenta vanishes because of this. So you cannot impose this commutation relation. Left hand side is 0, right hand side is not 0. Okay? So this procedure breaks down. Okay? So suppose I impose the phi is equal to 0 condition and then only look at the remaining degrees of freedom. You might have thought that should work. I mean, after all, this seems to look nice. So we should be able to do that. So what we want to do now is that let us assume A alpha t comma x and its corresponding canonically conjugate momenta is A dot, let us say beta. Okay, I don't need both vector symbols and this. So t comma y. And we want to impose that this is equal to I delta x minus y delta of beta alpha. Suppose you try to do this. I mean, this structure, half q dot square kind of structure tells you that this should probably work. It will work, but there is a problem. In order to actually work with physical degrees of freedom, it is not enough that you impose phi is equal to 0. You would have also imposed divergence of A is equal to 0. Because without that, A is not unique. I can do a gauge transformation and A will change. So you want to eliminate all the gauge transformation, degrees of freedom. So the moment you have put that and you take this equation, if I take the divergence of this equation, you run into trouble. So if I can flip this alpha here and beta here, without any problems. Now if I am going to do the d alpha of this entire equation with respect to x, I will have this with respect to dx alpha and I will have derivative of this with respect to dx alpha on the right hand side. The derivative of the Dirac delta function is a kind of a singular object, but it is not 0. Okay, acting on some function, it will produce the derivative of that function. But left hand side, we want to impose this to be 0. Okay, so we again run into trouble. Therefore, it tells you that these kind of commutation rules, these naive commutation rules you would have thought of, is going to run into trouble with the gauge degrees of freedom which are present in the system. So you want to circumvent that, and there are different ways of doing it. There is a very formal path integral method in which you can attack these problems, and that will maintain both gauge invariance and Lorentz invariant. The other method is to go back to this action, decompose it into harmonic oscillators and quantize the harmonic oscillators. That will work perfectly well, and finally go back and calculate this commutator to see what it is. Okay? So that is the, I will do both the approaches, but I will first start with the harmonic oscillator. Fine. So let us try that out. So we are going to work with the gauge, which we had already shown can always be imposed, such that phi is equal to 0 and divergence of A is equal to 0. This is our gauge. Then you want to look at that Lagrangian, half E square minus B square, and see how it goes. So in order to do that, let us take this A and again Fourier decompose it. So I have d3k over 2 pi cube. Let us introduce as usual qk of t into the I k dot x. And as for same reasons as scalar field, I am not going to worry about the fact that this is not a real quantity because we know how to handle it. I mean, eventually it can be decomposed into a real and imaginary parts, but even otherwise it will take care of itself. So what is A dot? A dot and curl of A are easy to write down. A dot is going to be just Same thing, qk dot, same thing. And curl of A is going to be I k cross this quantity d3k over 2 by the whole cube qk. I forgot to put the vector symbol. Q is a vector now, of course. qk of t e to the I k dot. Okay, so this is A is a vector, so Q is also a vector here. Okay, so this is what we have. And K, oh, K should be inside. Integral d3k 2 by the whole cube I k cross this one. Now let us ask what the A dot square and curl of A the whole square will do. A dot square is trivial because it's just like 5 dot square. So if you work it out, you will get half qk dot square. Okay. Now the curl square, you are going to take this, take another copy of this, and take a dot product. So that dot product will involve k cross qk dotted with another k cross qk eventually. Of course, originally it will be k and k prime, but there is a e to the I k dot x and e to the I k dot y, and they are going to be integrated over all d3x. That will give you the Dirac-Delta function. So this is what you will have. So this you can sort of circle it around, use the cyclic identity, and you can get it as qk. Okay, so let us take one term as real and the other term as star in order to get this curl of A in the proper form. So you will get qk vector star dot. So I am just rotating it cyclically. I will have k cross qk cross k. Okay. Now what is this? You use the rule of the middle term. So you have a, except for sign, qk and a k square. So there is a dot between these two. Then k and a qk dot k. Now qk dot k is 0. That is 0 because we have this condition. That condition tells you that this vector qk dot k should be 0. So that term doesn't contribute. So you end up getting here essentially a term which is going to go as k square mod qk square with a minus sign. Okay. And this is exactly what you want. When you work out the this object with a star on that, this is done in order to produce your e to the I k dot x and e to the I k dot, k prime dot x with opposite signs. So when you do the integral, you get a Dirac-Delta function on k minus k prime. Okay, that is already assumed in evaluating this quantity. So now you can go back and plug into what we have got there, and you can reduce everything down to a bunch of harmonic oscillators. It is not a surprising result because looking at the structure of that, you essentially have one term which is phi dot square and another term which is derivative of a square. It is just like your scalar field with a gradient of phi the whole square, except that here it is curved. And that curve becomes just an ordinary gradient because of this condition. So once you do that, your Lagrangian will become half, okay, or rather the action will become half integral. Your original action was dt d3x on E square minus B square, which was the Lagrangian. So now you are writing everything in terms of your harmonic oscillator. So you will have half integral d3k upon 2 pi d whole cube, integral over dt, the vector q corresponding to k dot, and it is complex, square minus k square q k dot square. So you work out the details of this. This is what you will end up getting. So these are again harmonic oscillators, but now the frequency omega square is equal to k square. So that tells you that these are massless excitations. I mean, the dispersion relation is E square is equal to B square. Okay, fine. Now it is good to do a little bit of window dressing here. If I solve this with the standard field equations, these are going to evolve as harmonic oscillators, and I can have its A's and A daggers, and I can go and plug it back in. The moment you do that, I have the full system. So just as, okay, everything is being called A, so let me call this script A. So the vector potential A will now become integral over d3k, the expansion, 2 pi equal to 2. Then we have, let me work with the small ak's and bk. Then I will have a 2 omega k from the normalization. Then I will have something like ak e to the minus ikx plus ak dagger e to the I. They are just like scalar field, component by component. However, the A's now have a vectorial nature, which we don't like. I mean, it is nice to have operators which doesn't have that. So the way we will work with it is to first introduce a set of vectors Ek, then you put an Ak in front, so that the vector part of it is a C number. And similarly, you have a AK dagger epsilon k here. But that is not good enough, because this has two components and you want to deal with both these components independently. So in order to do that, you introduce one more level of complication. What you do is you introduce two sets of polarizations. So you say it is A k lambda, E k lambda, and similarly here you introduce plus A k lambda dagger, E k lambda, and then in addition to this d3k, you also sum over lambda equals 1, 2. Now, this is a little bit of a mess, so let me pause and explain to you what is going on. You had here some vector, because you originally had a vector qk here. That qk is going to be ak plus ak dagger kind of thing, a minus k dagger, right? So it has a vectorial nature. Now, it has to satisfy for every k this condition. So what you do is you choose a coordinate system in which this is, let us say, in k direction of k. Then in the plane orthogonal to that, you introduce two vectors, epsilon 1 and epsilon 2. But if I go and rotate this k, these two things has to remain orthogonal. So your epsilons are all going to rotate. Therefore, the epsilons are implicit functions of k, so you put a subscript. You could have put it in the bracket, it doesn't matter. Epsilon 1 within bracket k. But this is as good. Okay? So you have, for at every point you have a k vector. Then in the plane orthogonal to it with some right hand rule or whatever, you introduce an epsilon 1 and epsilon 2 vector which depends on k. So for every k you have these two pairs of vectors. So that is what you denote by epsilon k lambda. The lambda is 1 or 2. So for every k there are two of them, lambda is equal to 1 and lambda is equal to 2. Okay? And in fact, to be very precise, this summation should be probably kept here. Let me write it as d3k here outside upon 2 pi the whole cube summation over lambda equals 1 or 2. So for a given value of k, before you start integrating over k, you sum over lambda equals to 1 and lambda equals 2, and then you integrate over every value of k. This is the way it works, but you understand what I mean. I mean, even if I interchange it the other way. So the physical meaning of this is that this k tells you the momentum and lambda tells you the polarization, in which is the direction in which the vector potential is, etc. Okay? So as a result of which, the AK lambda and AK dagger lambda now create and annihilate photons with a momentum k and a polarization index. I mean, you can have photons which are polarized in any one of the two states or superpositions of them, and that is coded in lambda. You may think that this is a kind of an unnecessary complication, but this has a lot of implications for the commutation rule when you finally work it out. Okay? So this is the structure which you get, and now you impose on this A and A dagger the standard commutation rules. So you are going to say that if I take A of k lambda, commutator A dagger of p lambda prime, this commutator will be 2 pi the whole cube derived delta function on k minus p and a Kronecker delta on lambda lambda. Okay? Because lambdas are just 1 or 2. This completely solves your problem. You can now go and construct your Hilbert space. It is going to be given by, you have to specify for me n k lambda. How many photons are there with a momentum k and a polarization lambda? Then it completely specifies the Hilbert space, and we have solved the problem. We have actually quantized it. We have also taken care that phi is 0 because we never dealt with phi. We have also taken care of divergence of A is equal to 0 by explicit construction. These epsilons are orthogonal to K. This is all which is there. Now suppose you ask the question, what happens to the commutation rules? This I will do in detail in the next lecture, but let me just illustrate or indicate to you what will happen. Suppose you try to calculate that any one of these commutation rules. Okay, for example, suppose I take A alpha and A beta. Okay, and calculate the commutator. In the case of scalar field, if you remember, we did exactly the same. We had A's and A daggers. A's and A daggers, we imposed this. Then we said that phi pi is equal to Dirac delta function. Now what will happen? In order to obtain that, you need one more relation. So let me just write that relation down. The relation is E for a given k and lambda, the vector, or rather take the alpha component of that, then take the beta component of k lambda, sum over the lambda, then you take k alpha, k beta upon k square. This will be equal to Kronecker delta alpha. Now what does this mean? This is a trivial relation actually. This epsilon alpha beta are unit vectors in these two directions. K alpha upon k is a unit vector in this direction. So this is like, if I think of k alpha upon k as some vector n alpha, so this is essentially, this is equal to n alpha n beta. So what I am saying is that epsilon 1 alpha beta plus epsilon 2 alpha beta plus n alpha n beta is equal to delta alpha beta. Now this is trivially true because if you choose this coordinate system in such a way that the alpha beta directions which we are talking about is x, y, z direction. Just take x, y, z directions and take alpha is equal to 1 for example. If alpha is equal to 1, in that direction either there is k or epsilon 1 or epsilon 2. Suppose epsilon 1 is there, then epsilon 1 will contribute to that. Then this will not contribute except when that is also equal to 1. This is not going to contribute, and epsilon 2 will not contribute. So it is trivially verified, and you can do that for every one of those indices. Okay? So there is just a formal way of writing this, but it turns out to be useful. When you work out the commutation rules, since you have already done it twice now, you should be veterans in that. You will be taking products of these quantities, this A alpha and A beta dot. The dot doesn't really matter because it is just going to give you an omega factor. And then when you are going to multiply two of them, you are going to pick up two root omega factors. That will have an omega factor in the denominator. Those two omega factors will cancel out. You will just have a half. Half doesn't matter again because when you are doing this calculation, there will be factors of 2 coming from it. And when you did it for the scalar field, what you would have got for the commutator would have been a structure like integral d3 of any one momentum upon 2 pi the whole cube. Then all the commutators will finally reduce to e to the I p dot x minus y. This is how you end up getting the Dirac delta function. When you take the time derivative, it will bring down an I times omega. Omega cancels out, but that I will hang around. That is how you get a factor I. And this would have been a I times Dirac delta function on x minus y. Suppose you repeat exactly the same thing. What will you get extra? You can almost guess. What you will get extra is that there is going to be these epsilons hanging around. And you will pick up 2 of those epsilons. Right? And you would be summing it over the lambda. Because just as you integrate over k. So I will do this in detail in the next lecture so you don't have to try it out. But what you will end up getting is that there is going to be a summation over lambda equals 1 to epsilon, let us say alpha. So remember that there is an alpha and beta index here which are carried by the epsilons. Epsilon of k or p, I am using p as the integration variable, p lambda, epsilon beta of p lambda. This is what you will get. The reason you get this is this encodes the fact that divergence of A is equal to 0. That is how we got this epsilon c. For this, you plug in this relation. That is, this sum is delta of alpha beta minus this quantity. So this reduces to I integral d3p upon 2 pi the whole cube e to the I p dot x minus y. This quantity will be delta of alpha beta minus k alpha k beta upon k. This is what you will get. This is not a Dirac delta function. So the right hand side of this commutator will have this structure. Now let us go and try this out. Suppose I take the d by dx alpha of this. So if I take a d by dx alpha of this, oh sorry, this should be p. P alpha, p beta, or p square. Where p is the integration variable. When you take the derivative with respect to x alpha, you will bring down a p alpha. What is p alpha acting on this? That is a 0. Because p alpha acting on this will give you a p beta. P alpha acting on this will give you a p square which will cancel out, and this is p beta. This is a projection operator into a plane which is orthogonal to the p direction. That is what it should be. It came from two dot products of epsilons. Epsilons are vectors hanging around in a plane orthogonal to p. So the divergence condition on the left hand side is automatically satisfied once you have got this. This expression is called transverse delta function. I mean, just as without this it is called a Dirac delta function, I times Dirac delta function. This is a transverse delta function. So what it tells you is that the right way to do the quantization of the electromagnetic field is not to impose A alpha, A beta dot is equal to Dirac delta function, but you have to say it is equal to the transverse delta function. This is something which you wouldn't have guessed. Now, if you just look at the Lagrangian, it takes a lot of intelligence to guess that this is what should be. Of course, in a way with hindsight, you can say that all the action is in the transverse plane. That for every k, it is in the transverse plane. But if you think in terms of harmonic oscillators, it is obvious. That is, when you go to the harmonic oscillator basis, the degrees of freedom are qk lambda, where lambda is 1 and 2, and they both are in the direction transverse to 3. These are the two transverse degrees of freedom which is physically relevant. So when you do the quantization, only the transverse parts of that should obey the commutation rule. So if you try to write it in a general term, there should be a transversality condition which is incorporated. Okay. So we will discuss some further aspects of this in the next lecture. So we are not meeting next week, the week after that. For example, you will find that if you take this A alpha, A beta, there is another problem that with normal Dirac delta functions, you know that we made a song and dance about the commutators vanishing for space-like separations, right? If you calculate it for arbitrary x and y, not on equal time. For arbitrary x and y, then for space-like separation, they have to vanish. You will find that as an error. Okay. So you have a alpha and A beta, whose commutator seems to violate causality. The solution to this is that A's are not observable. Again, they are gauge variables. So you should go and ask whether the electric fields commutators have that problem. Then you are sunk. And when you compute electric field propagators, you will find that nothing goes wrong. They vanish on space-like separation, but A's don't. So the mathematics and physics knows what is required and it will all adjust itself, but it is non-trivial. It is non-trivial because there are gauge redundancy in the system, so we will spend some time doing this. Yeah, that is topic. Questions?
So, when we prove this Goldstone theorem,
When I put what?
this Goldstone theorem, when you
Right, yeah.
So, this did not even require the symmetry that was broken to be an internal symmetry, right? It could have been.
Yeah.
So,
I only said that you need a state Q, which when acting on the ground state produces another state which is distinct. Okay. Now, if you use some normal symmetries like space-time translation, etc., you remember we also used that the PL is a sort of a conserved quantity in the proof of that theorem. So the normal space-time symmetries which you have are essentially generated by space-time translations or rotations. So that is not very useful.
but will there be a Goldstone boson if the system has such a symmetry?
This proof certainly doesn't go through because we are assuming that there are space-time translation symmetries based on PL, which are going to be standard conserved generators. That is how we put that PL commutator J is equal to DL of J.
Right. No, but so let's say so that's just for the translation. Suppose I'm looking at the rotational symmetry.
The same thing because,
because
those generators will also come in. Because you cannot have a system, I mean, I think there is a very general theorem that you cannot have a system which maintains, see, suppose you move a point and then you rotate without moving the point. There is some commutation relations which govern that. So you have to be very careful how you break it. So I don't know any system in which these things can be broken.
No, because for example, in ferromagnetism, when you gave that example,
Yes.
it is the rotational symmetry that the ground state didn't have, right?
That's correct.
So there was a space-time symmetry that was spontaneously broken there.
Yes.
And so I was wondering whether there should be a Goldstone mode for something.
No, there are lots of condensed matter systems where if you do not have a gauge field, I mean, which you usually don't introduce, then there will be a Goldstone. I mean, that is not surprising.
Here we show the gauge actually, and then we did the
Here.
commutation relations.
Yes.
If we choose some different gauge, then is
Yeah.
there a way to?
Okay. It turns out that is another thing which I didn't mention. The commutation relation which you compute depends on the gauge. Okay, so the commutation relations are not completely gauge invariant except when again you compute the commutation relation for physical observables. Like if you take the commutation relation between electric and magnetic field, that is like FLM component, they are gauge invariant, Lorentz invariant, and they are the same. But if you work at the level of gauge variables, like the vector potential, their commutation rules depend on the gauge. If you choose it in a different gauge, the gauge commutation will be different. Yeah, so that is why I thought I will discuss it in some detail, because it is usually you quantize the electromagnetic field in radiation gauge, do the semi-classical theory, and you keep moving. But there is some non-trivialities associated with doing the quantum theory of a system when there are gauge redundant variables. In fact, it's very peculiar. It's very peculiar that the most natural description of the world today seems to be in terms of gauge fields. Whether it is abelian or non-abelian, they are in terms of the gauge fields, which are simply not observable physically. By the same definition that they can be changed by the gauge transformation. If there is no way, people have tried to write down all the theories entirely in terms of observable quantities like FLMs. Even in QED, people have made that attempt. They look horrendously complicated. It is not elegant. It is not computationally nice. So it is a little bit of a mystery, at least in my mind, that why is it that nature always looks very simple in terms of gauge redundant variables, but ultimately you have to work in terms of observables which are gauge invariant. Why is it that you cannot formulate everything entirely in terms of directly observable quantities? That doesn't seem to be possible. And things are much worse in the case of non-abelian gauge theories, but that we will not discuss in this course. Any other? Okay. Someone should send me an email about your awareness.